What we are going to talk about is proofs with perpendicular lines. In the past couple lessons, we have been doing proofs using parallel lines. Parallel lines with transversals, what does that mean about the angles? How can you prove lines parallel, that kind of thing. Today, what we're going to look at is proving lines perpendicular, using perpendicular lines to prove other things, stuff like that. Now, first thing we're going to talk about is the distance from a point to a line, right? The distance from any point that is not on the line to a line is the length of a perpendicular segment from the point to the line. And it always has to be perpendicular. Because if you remember, distance, you were looking at the shortest distance from any 2 points, right? The shortest distance from point A to point B is this perpendicular line. If you take it and you turn it any at all, well, then you got to go farther, right? You know, if you're way out here, you got to go a lot farther than if you just go into it right here. Okay, so a perpendicular line is going to be the shortest distance from a line to a point not on the line. So you want this perpendicular segment right here. All right. Now, also, one other thing we do want to talk about, a perpendicular bisector. We've talked about these before. What this is just a perpendicular line that also happens to bisect a segment. So it's a segment bisector, and it's a perpendicular line to the segment, and so it's a perpendicular bisector because it's perpendicular and it bisects. Not all perpendicular lines are bisectors. Not all bisectors are perpendicular. All right? So we're going to take a look at this distance stuff first. We're going to do a couple examples using that. So in here, what we want to do, we'll just look at number one. Let's see. All right. We want to find the distance. It got all blurry on me. That's no good. There we go. We want to find the distance from point A to line BC. And it gives us point A right here at -3, 0. And here's line BC. And they also gave us several points on line BC that we could choose to find the distance to. And the question is, which one do we want? Well, we have this line, line AB. That's a nice vertical line. It's right on the grid line, so that's easy to see the distance there. We've got line AD right here. That's not too bad. And we've got line AC, this great long thing here. Well, which one does that theorem say is the distance? Which one is the shortest distance from the point to the line? It is the one that is perpendicular to the line, okay? So we don't want to pick AC because obviously that's real long and stuff. But we don't want to pick AB, even though it's, it's a perfectly vertical line. It's on the grid line and stuff. That's not what we're talking about when it says perpendicular. I'm not saying it's perpendicular to the axis. It needs to be perpendicular to the line. So what we're going to use is we're going to find the length of segment AD. All right. So let's see here. We have A is at -3, 0. D is at -1, -2. Come down here, we'll have some room to work on this. And remember the distance formula. Right? The distance, the length of segment AD is equal to the square root of the difference in your x's. So x1 minus x2, so that would be -3 minus -1. So -3 minus -1 squared plus the difference in our y squared. So let's see, our y values, we have 0 minus -2. All right. So 0 minus -2 squared. All right, and now let's work this out. That's the square root of, let's see, -3 minus -1. Well, when we subtract a negative, remember that's the same thing as adding the opposite. And we're going to do that over here too, add the opposite. So that's -3 plus 1. That would be -2 squared. Plus 0 plus 2, which is going to be +2 squared. All right, -2 squared. A negative times negative is positive. 2 times 2 is 4. So we have the square root of 4 plus 2 squared, which is 4. And so this gives me AD is the square root of 8. But we can simplify that. So let's simplify the square root of 8. Let's see, remember we do this using prime factorization. So I'll just switch colors. I'm going to do that right here. So we have the square root of 8. Factors of the square root of 8 would be the square root of 4 and the square root of 2. 4 is a perfect square, right? The square root of 4 is just 2, and that's out from underneath the square root. And 2 is prime. So square root of 2 and the square root of 2. So we have that the length of segment AD is equal to 2 times the square root of 2. And so this is the distance from point A to line BC. Is going to be 2 times the square root of 2. We're looking at segment AD there. All right, so let's do another example. Let's take a look at problem 2. Again, we are still looking for the distance from point A to line BC. Here we have point A is down here at -3, -4. Let's get this focus. Okay, and line BC is way up here. So which of these 3 points do we want to use? Do we want to use point C? Do we want to use point D? Do we want to use point B? Remember, distance is the length of the segment that is perpendicular to the line. So the only one that's perpendicular, that would be this one right here with the right angle in it. And so we're going to use, again, segment AD. It is not always going to be segment AD. It's whichever one is perpendicular to the line that we're going to. All right, so let's come down here and let's work this out. All right, so this is problem number 2. Again, we're using segment AD, we said. So AD, the length of AD, see there's no bar above it, is equal to the square root of the difference in our x's. So -3 minus +3. Or you could take it and do it the other way, +3 minus -3, it doesn't matter. -3 minus +3 squared plus the difference in our y's. So that would be -4 and +2. So -4 minus +2 squared. All right. Let's see, -3 minus 3, it would be -6 squared plus, oops, I forgot my parentheses there. -4 minus 2 is -6 squared. All right, so now I have the square root of -6 squared would be 36. And that's -6 again, so plus 36. 36 and 36 is the square root of 72. 72 is not a perfect square, so I am going to have to simplify this again. Same thing we did right here, only with 72. So square root of 72, see factors of 72, this would be 9 times 8. And the square root of 9, the square root of 8, because it's the square root of 72. 9 is a perfect square. So since 9 is a perfect square, I can pull this out from underneath the square root as just 3. 8 is not a perfect square. So that will be the square root of 4 times the square root of 2. 4 is a perfect square. So I can do, or I could do this. If I forget that 4 is a perfect square, I can say 2 and square root of 2. And if we do it like this, that's fine. What we're looking for, if we don't have it broken up as perfect squares, we go all the way down like this. We're looking for pairs. What do I have a pair of? Well, I have a pair of 2's. I have one right here and one right there. Pair of square root of 2. Square root of 2 times the square root of 2, that comes together, and that is just 2. So I have 3 times 2 times the square root of 2. Well, 3 times 2 is 6, and then I have the square root of 2 left over, so 6 times the square root of 2 is the length of segment AD. All right? And there's our distance, 6 times the square root of 2. So not too bad, not too bad. The important thing is make sure you find the line that is perpendicular to the other the other line. Well, that's the one we want, the segment that is perpendicular to the other line. So what I would like for y'all to do, I would like y'all to pause the video and work out 3 and 4. See what you come up with. We're looking for the distance from point A to line BC on both of these, point A to line BC. And work it out, then come back to the video, check it, see if you got it right. All right, so you're back. Let's see how you did. So number 3, we are going from point A to which point do we want? Perpendicular line, perpendicular line. Nope, there it is, perpendicular line. We're going from A to C this time. So from A to C, let me do this one green because why not? All right, so segment AC equals the square root of, and let's see my difference in my x's, so that's -3 and +1. So -3 minus 1 squared plus the difference in my y's, which is -3 and -1. So -3 minus -1 squared. All right, let's work this out. -3 minus 1 would be -4 squared. -3, okay, remember we have to change this to adding the opposite. So this would be -3 plus 1, which would be -2 squared. All right. -4 squared is 16. -2 squared is 4, so I have 16 plus 4, so this is going to be the square root of 20. 20 is not a perfect square, so I'm going to have to simplify this if I can. And so I have the square root of 20. Factors of 20 would be the square root of 4 and the square root of 5. I know the square root of 4, that's a perfect square. That is 2. And 5 is prime, so I just have 2 times the square root of 5. So the length of segment AC equals 2 square roots of 5. And so there's number 3. Let's take a look at number 4 real quick. Number 4, we are going from A to, there's our perpendicular line. We're going to looking for the length of segment AC again. All right. So the length of segment AC, and this is going to be the square root of the difference in our x's, which is a 1 and 3. So that would be 1 minus 3 squared plus the difference in our y values. There we go. That would be 3 and 2. So 3 minus 2 squared. So 1 minus 3 is -2. So I've got -2 squared plus 3 minus 2, which is 1 squared. -2 squared is 4. 1 squared is 1. And so we end up with a square root of 5. 5 is prime, which means I don't have to mess with any of this simplifying here. It's just going to be the square root of 5. So the length of segment AC is the square root of 5. All right? So that's not too bad. Not too bad. Now, we do have some other stuff in this lesson, so let's take a look at this other stuff that we had. We had some theorems here. The first theorem we have is the linear pair perpendicular theorem. What this says is that if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Right? So since angle 1 and angle 2 are a linear pair, and since angle 1 and angle 2 are perpendicular, congruent, then line G is going to be perpendicular to line H. Okay, and if you think about it, this is a linear pair. If these two, that means they add up to 180 degrees, right? If these two lines are angles, if these two angles are congruent, that means that this is an angle bisector because bisecting this straight angle. So half of 180 degrees is 90 degrees, which makes these two both a right angle. And so the lines are perpendicular because they intersect at right angles. Okay. Next one, the perpendicular transversal theorem. Let me see how much of this to touch. what this says, in a plane, always dealing with planar stuff, not two-dimensional. So we're just doing two-dimensional, not three-dimensional, because it's in a plane. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So over here in our picture, we've got two parallel lines, H and K. Since J is perpendicular to H, then it is also perpendicular to K. And if you think about this with the theorems you've already done, since these two lines are parallel, that makes these two angles, these corresponding angles, congruent. So if this is a right angle, this one is going to be congruent to it. It's also going to be a right angle. So both of these lines will be perpendicular to line J. All right. Last one we have is lines perpendicular to a transversal, which is very similar to the previous one, slightly different. In this one, what it is, if you have two lines perpendicular to the same line, then they are parallel to each other. So since line M is perpendicular to P and line N is perpendicular to P, M and N are parallel to each other. Because if they're perpendicular, that means your corresponding angles here are both right angles, and if corresponding angles are congruent, then lines are parallel. All right? That would be the converse, the congruent angle, corresponding angles converse, right? Okay, so let's see how we can use these theorems for stuff. What we want to do on 5, 6, 7, and 8 is determine which lines, if any, must be parallel. All right, and then we need to explain our reasoning. Let's see if I can get a better focus. Not much. Oh. So here we go. We have number 5. We know that P is perpendicular to S. We want to know, is anything parallel? Well, we have no idea how Q intersects S, do we? We don't know if that's the only thing that could be parallel is P and Q. But we don't know if this is perpendicular. We don't know if this is acute. What is this? We don't know. And so since we know nothing about this intersection over here, then we know nothing about whether any of these are parallel. So as far as we know, none of these are parallel. None of those are parallel. Number 6, let's see, we have lines R, S, P, and Q. The only ones that could possibly be perpendicular are R and S or P and Q. So let's see, R and S. R, we have some perpendicular lines going on there. But S, we have no information about how S intersects these two lines, do we? So we have no idea about S. So we can't say R and S. Let's try P and Q. P and Q are both perpendicular to line R. And so since those are both perpendicular to line R, that looks familiar. We talked about that a minute ago. Let's see here. That's down here. It is. Lines perpendicular to a transversal. So since these two lines are both perpendicular to the transversal, they are parallel to each other. So that's what this is. Lines perpendicular to a transversal theorem. So we can say that P is parallel to Q. We do have to explain our reasoning. That's in the instructions right there. Explain your reasoning. So since P is parallel to Q because of the lines perpendicular to a transversal theorem. Smell that out. I can't spell. Lines perpendicular to a transversal. And this is the theorem. All right. So pause the video, see what you can't do with 7 and 8. All right, so let's take a look at 7 and 8. On this, we could have M and N. We could have J and K. Let's see here. M and N, there we go. M and N are both perpendicular to line K, which by the lines perpendicular to transversal theorem, they're parallel to each other. But also, you notice right here, J and K are both perpendicular to M, which means they are also parallel. So we're going to put these both together. So we have M is parallel to N, and J is parallel to K. Both of these are because of the lines perpendicular to a transversal theorem. All right. And number 8, let's see how you did on that one. Let's see, nothing right there. But, we do have this. We have these two right there. Remember, we have these two lines of angles form a linear pair, and they are congruent. And so what that means is that N is perpendicular to S because of the, what was that called? That was called the linear pair perpendicular theorem. So linear pair perpendicular theorem. Yes, I use abbreviations and symbols because that way I don't have to spell them. I misspelled the transversal. Okay. So since this is perpendicular, that means M and N are both perpendicular to S. S and T are both perpendicular to N. And so that means M is parallel to N. And it means that S is parallel to T by the lines perpendicular to a transversal theorem. And it's perpendicular to a transversal theorem. So that is proofs with perpendicular lines. You can use perpendicular lines to prove things parallel. We also use perpendicular lines to find the distance from a point to another line. And there's your theorems again. So hopefully you found that helpful, and I will catch you next time.